Okay guys, so here we are learning how to solve complex force problems involving all the forces that we've learned about so far. So within this lesson you're going to use a lot of what you've learned throughout the entire unit to solve various problems. So let's put on our date, October 26th. It's my daddy's birthday. 2017. And so in order to solve these problems, I made up a list of strategies and steps that you could follow to solve or get started on any of these problems. So I have written here, draw a free body diagram of each object involved. Draw a free body diagram of the system, which is all the objects involved. Consider the forces acting on the system, or consider the forces acting on the individual object, and that's going to depend on what you're looking for. And then what also might help, or instead maybe the GRASS method. In some of your homework they ask you for kinematic quantities like velocities and distances and displacements. So in those cases you might want to use the GRASS method to guide your problem solving. Okay, so let's get started. What I'm going to do is, because each of the questions is pretty lengthy, I'm going to do each example in its own video, so you can choose the next video if you are good with whichever one you're working on, and then you can go back into the videos to see which ones you need. Okay, so let's get started. So this is a question you've seen before. You saw it last week when I did a screencast of solving systems, and then on the quiz you also saw this question again, but now we're going to add in that friction component so that we can solve it in a more realistic setting. So here we go. Example 1. In an investigation, students place a 0.80 kilogram cart on a table. They tie one end of the light massless string to the front of the cart and run the string over a frictionless pulley and tie the other end to a 0.20 kilogram hanging object. The coefficient of kinetic friction between the cart and the table is 0.15. So there's that added element of friction. The questions are, determine the acceleration of the system, and then calculate the magnitude in the tension of the tension. That would be tension force. Okay, just to clarify. So let's go ahead and solve part A. So because it's looking for the system, that means we're looking at the masses as a whole. So what we did last week was we learned how to draw those masses in a train-like setup. So kind of like the train question we did. So this is mass 1, this is mass 2, this is mass 1, this is mass 2. Okay, and then they're attached by a string, and then the direction of motion can now be like one way, horizontally. So the forces that are acting in that direction, you draw them in. So Fg2 would be the force going down on the second mass. And then the other one, of course, we have tension in the middle, but because these are acting within the system, so in between the two objects, then they're going to cancel out and they're not going to contribute to the acceleration. And then the new one we have here is this kinetic friction force acting opposing the direction of motion. Okay. So step 1 would be to draw the system diagram. Okay, so that's done. Step 2, we're going to write out the F net equation for the system. Okay, so what that means is I have to look at the whole system as a whole, so the total mass, and then the forces that are acting on the outside of the system, okay, to make it accelerate. So F net is equal to MTA. MT is the total mass. So let's say that everything gets moving this way. You could say it's going the other way. If your acceleration ends up being negative, then you've just assumed the wrong direction to start with. So we're going with this way for now. So if that's the positive direction, then FG2 is acting in that direction. FK is acting in the opposite direction, and that's it for that direction of forces, because the tension forces cancel out. And now we can plug in our formulas for these forces. Since this kinetic friction is acting on the first mass, then we're dealing with the normal force associated with the first mass. So recall, if we were to draw a free body diagram for this guy, we would have tension going that way, kinetic friction going that way, the normal force that way, and the gravitational force down. So the normal force, because the object's not accelerating in the vertical direction, is equal and opposite to the gravitational force of mass 1. So when we go to plug in down here, we're going to be able to put in m1g, because that's equivalent to the normal force. But first I'm going to rearrange this bad boy for acceleration, because that's what I'm looking for. And I'm always going to rearrange before I sub in numbers, so as to not confuse my reader, aka me. So we're going to go m2g, take away mu k, and now Fn, which is just the gravitational force of mass 1, is m1g. We can change that, and then that's all over the total mass. And all now I have to do is sub in my numbers. So a little arrow to guide my reader as to where to go next. So that was the end of step 2. Step 3 was to solve, okay? Solve for your missing quantity. Okay, so we're going to continue there. Now plug in your numbers. Mass 2 times g minus mu k, which is 0.15, times mass 1 times g all over mass 1 plus mass 2. So if I go ahead and compute that, I'm going to cheat, I'm going to sneak a peek because I've already solved this question. My accelerations end up being 0.78 meters per second squared in this direction. Because it ended up being positive, then my convention was correct. Okay? So that is the answer for part A. Part B, we're looking for the tension force. So I can't go back to this diagram to look for tension because tension ends up canceling out. So I know that tension occurs in the individual free body diagrams. So I'm going to choose the simplest mass out of these two to analyze Ft, which is mass 2. So if I draw a free body diagram of mass 2, I got Ft up and Fg2 down. Down is being positive. And then from that, I'm going to write my net force equation on block, or on this mass here. So F net equals Fg2 take away Ft, and that's equal to the mass that we're talking about, so m2 times its acceleration. Its acceleration is the exact same as the one we found here, because if the system is accelerating, then each of the individual objects is accelerating. So we're going to use A right here. Now I have to rearrange this equation for Ft, so I'm just looking at this portion of it. So rearranging, the magic happens. That comes over here, this comes over here. FG2 take away M2A, which is M2G, take away M2A. And if you want to go back to your grade 10 factoring abilities, you can factor out that M2 and just get G minus A. You don't have to do that, but it's impressive. Plugging in your numbers, you get a tension force of 1.8 newtons. And now they only asked for the magnitude way back up here, so I don't need the direction. And there you have it. There's example 1 in a nutshell.